Thank you. It's great to be here. And the title of my presentation is Financial Software on GPUs between Haskell and Fortran. And this is joint work with Christian Anderta, Joost Berthold, Fritz Hangelein from University of Copenhagen, Department of Health Science, and Alain Frisch and Jean-Marc Eber from Lexity. So in this presentation, I'm going to describe a case study in which we have taken a real-world pricing kernel, and the first goal was the main goal was to parallelize it on GPUs. So while doing this, we had the three main objectives, and the first one was a very pragmatical one, in that our partners from XCP wanted to know, well, just what to expect from, if they would like in the future to move their code on GPU, what kind of speedups do they get? And, sorry. And then, the second goal, in a more scientific perspective, was that we'd like to see whether this application can be parallelized via a set of functional inherently parallel constructs, and how easy or difficult is it to express the whole algorithm in such a language. And we are using Haskell here as a high-level language, source language. And finally, the third goal was to, once we have this program written in high-level language, then in which parallelism it's obvious to the user or available to the compiler, then we'd like to know what are the optimizations so that this program can run efficiently on GPUs. And here we are talking more about compiler-like optimization. So this optimization should, in principle, be done automatically to ease the use, the burden on the user shoulder. So to summarize in perspective, we want a hardware-independent language, and we would like the user to mainly be focused on specifying the algorithmic invariants. And the consequence of this is that if the algorithm is inherently parallel, then we expect that this should also be a property which is easily derivable from the implementation. And the compiler should be the depository of intelligence that will allow this code to run efficiently. And, well, this is not something new, but this is motivated by work in automatic parallelization of imperative programs, in which the other direction, basically having a very optimized sequential program, which runs very well sequentially, it's very difficult actually to go into inferring whether some loops are parallel or not. So we are going into the hopefully easiest direction in which we exploit the parallels available and we just try to optimize the program. So this being said, what is the problem that this application is solving? Well, we have a financial contract which is specified in terms of some dates and some stocks that we are calling underlines. So an example of such contract can be that you receive $100 next month and return some amount in 1 year time plus some function or formula in terms of these stocks measured at these dates. So the question is, we'd like to compute what is the value of such a financial contract now. So how this algorithm works? Well, it has 5 stages. First, we compute a quasi-random Sobol vector, uniformly distributing 0, 1. And then we transform this into a Gaussian distribution by numerical integration. And then we use a Brownian bridge to correlate all dates for each underline. And then we correlate among different underlines using Black's calls. And finally, we apply a Monte Carlo aggregation with products, payoff, and discount in order to average things out to get a good approximation. And this figure is supposed to show that, well, we have one big parallel Monte Carlo direction. And then each of these other directions, number of dates and number of other lines, have some parallels in it, but in at least one stage there are sequential. So this is how it looks if you are writing this program in Haskell. So it's visually pleasing. And more importantly, you have the parallel constructs map and sum available already in the program, so you can exploit the parallelism of the Monte Carlo iteration and possibly some other inner parallels. So now I'm going to jump. So finding the language suitable, well, maybe I should say that this cannot be expressed only with a typical functional parallel constructs such as map, reduce, zip width, zip, and so on. You would also need for the Brownian bridge monadic code because it's rather difficult to write it recursively. Even if you can write it recursively, it would be presumably very difficult to translate the recursion into a loop that it understood by GPU. So now we are looking at the optimizations that we have found most useful in this context. And the first one, without, it is not a big surprise that we have found that map fusion and distribution is an important choice. So these are two forms of a semantically equivalent program. A map reduced program can be rewritten by first distributing the list among the number of processors, and then performing the sequential computation on each of these processors in parallel, and then reducing in the end the results among all processors. So now we have two ways in which we can write the previous program. So one way would be to distribute the map across each function, right, and then reduce in the end. And the other way, expressed here in kind of a Fortran combined with pseudo code OpenMP, in which each processor it's allocated some variables and it's reusing those variables. Right? So now these variables are allocated per processor, and they are used across various iterations that happen to be on the same processor. So the difference between these two codes is that if you are looking at the memory complexity, the memory size that you need to execute this program is proportional with n, which is the number of iterations, while in this case it's proportional with p. So what you would expect to have is that if you are running this on GPU and you can fit these local variables into the fast memory, which is small, then you would hope that you can get a compute-bound behavior of your program, while in this case, you probably are going to get a memory-bound behavior because you are instantiating all this list over the whole Monte Carlo iteration space. So, well, why to do? Is there any reason for which you would like to do loop distribution, map distribution? Well, this will allow you to have smaller kernels, which conceivably can be better optimized, and they put less register pressure. So, for example, here our Gaussian function is looking at its turn as a map with a Gaussian element. So we have a map of map which you can flatten up. The only cons is that this has memory size proportional with n, and as we have said, and typically leads to a memory-bound program because we can only try to hide latency, but this will not eliminate completely. So the second version, well, we expect to have a compute-bound program, but it increases register pressure, and in the general case, it's not applicable. So if those local variables do not fit in your registers, then you have to allocate them anyway in the global memory. So this means that you are going to do anyway array expansion. So this will lead to the previous case of map distribution. So I'm going to show some numbers in the middle of the presentation. So for the experimental setup, we have used a gaming system and a mobile system. The results that you are going to see, you should take them with a grain of salt, because, for example, the gaming system is using the latest GPU with 1500 cores, but it's using a rather old CPU. So it doesn't mean that these numbers will translate if you are running them on different systems. And this is actually this laptop here, the mobile system, with a Quadro 2010 GPU. We have used standard GCC with optimization -03 and NVCC with the default optimization. And the speedups were measured with respect to sequential CPU runtime, which means we haven't, the sequential, this doesn't include any kind of SSC instructions, optimizations, or anything like. And we're average among 20 independent runs. So again, this is not to do a comparison between CPU and GPU architectures. It's just a way to show that we have a rich optimization space and to look at the trade-offs. So with respect here with blue, you see the basically left fused version of the code. And with red, you see the vectorized version of the code. And we are estimating 3 contracts. Simple means that we have 1 underline and 1 date. Medium means that we have 3 underlines and 5 dates. And complex means that you have 3 underline and 367 dates. So as U and B increase, this means that those temporaries are now 2-dimensional arrays with, for example, in the second case, first size 3 and the second 5, so 15 size vector, and here even bigger. So the interesting part in this is that when U equals 1 and U equals 1, you see that here you get a compute bound program. And the vectorized version, there is a significant gap between these 2 versions. And as you are increasing the dimension of the inner vectors, then you observe that the benefit of doing this tops up, because basically in this case you are paying with you are putting more register pressure, so you are paying with a smaller degree of parallelism. And finally, for the complex case, you cannot run it fused. And this is when you are using double precision flows, so pretty much this is what we expect, because the slowdown is between 3 times to 4 times. And these are the digits. Again, this take them with a grain of salt, probably lower than this. Okay, so we have finished with the first, I would call it medium level optimization, fusion distribution. And now we are going to show a high level optimization, and this refers to the well-known optimization of strength reduction. So the typical way in which you will see this in a compiler book is something like this, in which here you are using a recurrent formula to compute K, recurrent addition. But the problem with this is that if you want to parallelize this loop, that's not possible in this form, because this gives a producer-consumer relation with the previous iteration. So the previous iteration is producing something that you are consuming. So in order to parallelize this, you are going to do induction variable substitution, which basically replaces this recurrent formula with a closed form solution in the loop index R. And now you can parallelize this because you have not written up the dependence. However, here multiplication is more expensive than the simple addition here. So you are paying for parallelism with performing a costly operation. And we have an example of strength reduction in our code, and this corresponds to the Sobol algorithm, in which we can see that we have a Sobol formula which is independent, which means it can be computed only by giving the number of the Monte Carlo iteration. And then we have a recurrent formula which relies on having the previous element computing with the previous Sobol number, and then from the previous number and the function which computes a new vector, it aggregates it with zip, it with XOR, and computes the next number. So this is much lighter than this one, but this one corresponds to an embarrassing parallel algorithm if you are writing something map of Sobol independent on a range in the current iteration. This will give you an embarrassing parallel algorithm, but it involves more computation, while you can still write it in parallel by, for example, using the recurrent version by taking Sobol independent the first number and then computing the rest with a prefix sum, with a scan, with the Sobol recurrent formula. So this, because this operator, this can be decomposed into an associative operator. For example, look here, this is a zip with XOR, and XOR is associative. Then this will lead to a low-end depth parallel algorithm, which performs less computation. So we'd like to know whether we can have the benefit of the both, and certainly we can. If we have many more iterations than processors, then these are two semantically equivalent programs, and then replacing F here with Sobol independent would give this equivalence, and then we can replace the sequential computation of map with Sobol with Sobol rect. And now here we have the efficient. Here basically we are amortizing the computation of one Sobol independent formula, which is expensive, with n-1 computation of the fast formula. So in essence, we would like the user to express his invariance. Basically, the fact that Sobol independent and Sobol recurrent are in the strength reduction relation. And then the compiler can basically generate this code in which it chooses in which the most efficient version for the hardware and data is chosen each time. For example, if you have significantly more iteration than processors, then we choose this formula. Right? If we have roughly the same number of processor as iterations, then we use Sobol independent because we like to execute this in parallel. And for the sequential case, we will choose the chip formula. However, we will not want to burden the programmer with reasoning about the optimization, space, and cost, and to start writing very complicated code to tune his algorithm to the hardware and to the sensitive data. So we just observed that this information it's enough for the compiler to optimize the code in this manner. So now I'm presenting the impact of strength reduction, meaning I'm comparing the two versions, the relative speed up with respect to the version which it's run with only strength reduction off and with all the other optimization on. So we can see for U and D equals 1 that we have here almost a speed up of 4. And then the speed up reduces because basically what happened is that those kernels have different weights in the total runtime. So once you start changing U and D, they will weight less or more. So this changes its data independent. So we get a speed up as high as 3.8, and also this behavior is more or less similar on the other GPU. So the question is now, why not let the user choose? Well, because optimization are data type sensitive, depend on n, and we have seen that, for example, also fusion or distribution depends on the size of the inner vectors. Because optimization are hardware dependent, right? In one way, you'd like the program to be optimized for sequential, and in another way for parallel execution on various platforms. And the third reason, and most important, is because the user might optimize the code too well, and then you lose parallelism. For example, this case can be seen in several benchmarks from the Perfect Lab suite. And the problem here is that this computes kind of an inner filter, but this temporary array in which are stored the indexes which pass the test are actually declared globally. So the compiler will, in order to parallelize this do loop, the compiler will have to choose to prove that any index, any element from index which is read here has been written in the same iteration over here. And the problem is that this len is not a closed form induction variable, which means it cannot be expressed just in terms of I because it's conditionally incremented. So the compiler will not be able, typically in most commercial compilers and also research compilers, to represent, to prove this invariant. And here we are seeing in the same way that it's very difficult to actually recognize a scan. Both of these are versions of scan, and also the compiler will be unable to do this because firstly this looks like a reduction, but however the result of the reduction is read somewhere else, so this is not a reduction and cannot be optimized with traditional techniques. And this looks like a data dependency of distance 1, so this also looks all foolish and sequential to the compiler. So finally, the last optimization, and actually the most impactful one, refers to memory coalescing. And this refers to a case like this, in which you have a map which is parallel, and inside the map you have a sequential code. For example, if this operator is not associative, then scan with this operator cannot be parallelized. So it corresponds to a case like this, in which you have a parallel for and then a sequential for, and then you are doing something with an array of ij. And the problem here is that each core, right, will access the inner vector of this array. So each consecutive core will access memory which are apart with m elements, meaning that, for example, when such data transfer occurs, then you need 16 independent data transfers to bring the data to the processors. And this is a non-coalesced success, and you are paying a lot for this on the GPU. And we would like to transform the code in a manner that looks like this figure, in which 16 consecutive cores are accessing consecutive memory locations. And we give a very simple transformation technique in which basically we are distributing the parallel dimension of the array, right? So we keep a number, we basically create an innermost dimension of size 16 to enable coalescing, and we keep also the rest of it as the first dimension array. So we apply this transformation, T of xy equals x divided by 16, y x minus 16, uniformly to the code, and this will fix coalescing, as in this case. This will give coalesced success. And this might happen. It might happen that fixing coalescing in this way might destroy it in another, because, for example, here it's an uncoalesced success, and here it's a coalesced success. So doing this transformation uniformly will fix the coalescing here, but will destroy it here. However, this can be fixed with a transposition after doing this loop. So the relative speedups with memory coalescing on and off are pretty significant. So for example, with a medium contract on floats, you get a factor of over 30 speedup with memory coalescing on rather than off. And on the other hardware, we get, well, as high as 20 times speedup. So this is a lower level optimization in the sense that it's not, you wouldn't expect the user to do this, and it might be actually quite unfeasible to do something like this in a language like Haskell, and hence it's suited to be implemented in an optimizer compiler repertoire. So in conclusion, we have seen a real-world application that shows good speedups on GPUs, and we have learned that it can be expressed in a DSL that supports the usual second-order functions, and for one basic block we needed monadic code. We have argued that the user should mostly be concerned with expressing algorithmic invariance, and the compiler should be able to take advantage of this algorithmic invariance. And we have also demonstrated the rich optimization space that is best exploited at compiler level because there is the whole information. Thank you very much.
Thank you. We do have time for questions.
So you showed us quite a bit of Haskell code that looked like, well, ordinary Haskell code, which is great. But I was a little hazy about how you compiled that, how you turned that into code for your GPU. And you showed us lots of transformations to optimizations. I was unclear about whether any of those were automated or whether they were ones that you simply applied by hand.
No.
And whether you think they're open to, I mean, so here you suggest that they might be best exploited at the compiler level. But I'm interested in whether you think that would be straightforward or, you know, really very, very difficult. Could be anywhere on that range.
So no, the optimization were indeed performed by hand. Okay. We have just tried to, we could have optimized this code much better. We restricted ourselves to a minimum of, well, I would say simple enough optimization that they can be integrated quite fast in the optimizing compiler. With respect to the language, well, we have just used Haskell for expressing the algorithm, and sure that we are thinking on an array calculus language rather than lists, right? For easy understanding, we have used lists in the presentation. We do not have yet this language, but we are working on it. And with respect to the implementations, well, I have chosen to show basically mostly optimization that can be applied to map-reduce programs. So, for example, this optimization here, because you have a map, then you are, in most of the cases, the indexing here, J or whatever else it is not going to depend on I. So this optimization can be generically applied to any map that works on a multi-dimensional array.
So what I meant was, how did you get from this code to CUDA code or whatever you're running on your GPU?
Oh, by well, working or building a small language. This is what we envision, building a small calculus, array calculus language with a typical parallel constructs, right? And then keeping it, building an abstract syntax tree, doing some compiler optimization on it, and then generating the GPU and OpenMP code.
And this is what you did? Or
No,
plan to do?
This is what we are planning to do.
Okay, so let me ask you again, how did you get from this code to CUDA code?
Oh, by hand.
Ah, thank you.
So the graphs are Fortran CUDA, or are they Haskell with CUDA called via FFI?
No, by hand transformation. We use OpenCL.
Okay.
So all the graphs are from OpenCL. Okay. Well, it's fantastic to hear that the set of primitives we talked about, which we know and love, map, scan, fold, are sufficient for what you want to express. So if that is the case, is the core language supported by Accelerate sufficient for the things you described? And if so, why make a new array calculus language instead of a new Accelerate backend? It's very easy to make new Accelerate backends.
Sure. Well, that's because we have tried to translate this code to Accelerate, and we have not been very successful. In my limited understanding of Accelerate, you cannot put in your expression language a map or a scan. So you cannot have a map and then a scan which you are saying, I would like this to be executed sequentially.
So you want nested parallels?
Yes.
Okay.
Was the question?
That was just
okay, that was
the easy answer.
Okay, very good. So I think we'll have to stop now. So thanks, speaker again.